Guys, welcome back to TechDose, and in this video we will look at the maximum sum of three non-overlapping subarrays, which is from Leetcode number 689, and we will be looking at the intuitive dynamic programming solution. So the prerequisite before watching this is to watch my video on 01 knapsack DP. So I have already made a recursion and memoization along with tabulation, 3 different videos for 01 knapsack. I will be sharing this link in the description below and also in the I button. Now let's read the problem statement. In this problem, given an integer array nums and an integer k, find 3 non-overlapping subarrays of length k with maximum sum and return them. Return the result as a list of indices representing the starting position of each interval that is 0 indexed. And if there are multiple answers, we need to return the lexicographically smallest one. Now if you look at the constraint, then we have a total of 2 times of 10 to the power 4 items. Each of the item will be less than 2 to the power 16. So everything is within the integer range. And you will find that the nums length by 3 is always greater than equals to the k value. That means it will always be possible to get to an answer. So looking at the constraint, you can be sure that an n square algorithm is not going to work here, because an n square algorithm will be 4 times of 10 to the power of 8, and we need to write an algorithm less than 10 to the power 8. Okay. Now let's look at an example for better understanding. Let's say that we are given 8 items in a given array and the k value is equals to 2. Now we need to find 3 non-overlapping subarrays with the maximum sum, and we need to return the list of the start indices of all these subarrays. These start indices should be lexicographically smallest in case if there are multiple answers. So if we look at the given problem, then how many subarrays can be present of size k? So if the n size is 8, then using the sliding window, you can form n minus k plus 1 subarrays with size k. So there will be 7 subarrays. If I can give a few example, then the subarray of size 2 will be 0, 1, then you will have 1, 2, then you will have 2, 3, and so on, right? The last one will be 6, 7. This one will be the last one. So out of all these combinations, we need to find 3 subarrays which are non-overlapping. That means they do not have anything in common and their sum is maximum. So you will be finding 2 such candidates. One candidate will be 0, 1, 3, 4 and 5, 6. If you add all these values 1, 2, 2, 6 and 7, 5, it will be 23. Another candidate is you pick 1, 2, 3, 4 and 5, 6. In this case also you will get the same sum as 23, which is max sum. But if you compare these 2 indices, what are the start point of this first one? It will be 0, 3 and 5. For the second option, the start point is 1, 3 and 5. So if you compare these lexicographical ordering, then you will find that 0, 3, 5 is actually less than 1, 3, 5. Because 0 is less than 1. So lexicographically 0, 3, 5 will be smaller, and therefore even if we have multiple answers, we will always be returning the one with the smallest lexicographical ordering, right? So it will be 0, 3, 5. Now in this particular case, if you want to generate all possible subarrays of size k and then find out the result for 3 non-overlapping subarrays, then what we need to do is we will be requiring to run 3 loops. The first loop will be running from the first subarray to the 7 minus 2th subarray. That means the 5th subarray. The second loop will be running from the second subarray to the 6th subarray. And the last loop will be running from the third subarray to the 7th subarray. So we need to run 3 loops, and we need to check that the end of the previous subarray must be less than the start of the next subarray. That means they will be non-overlapping. And you need to find 3 such subarrays which are non-overlapping, and we need to maximize the sum and track the indices. If you follow this brute force approach, then it will be n cube solution, and we have seen in the constraint section that n square was already greater than 10 to the power of 8, and that is why n cube will definitely be greater than 10 to the power of 12. So this is not a good solution. It will give you TLE. Now in this particular case, if you think about another brute force solution, then that would be if you are present at a index, then you basically have 2 choices. Whether you start a subarray of size k at this particular point, or you don't start a subarray at this point. So if you start a subarray of size k at this point, you will go to the I plus kth index and again start making your choices. Otherwise, if you don't include here, then you will go to the next index. It is the same concept as the knapsack. If you follow that strategy, then given this array, if the general index is, let's say, at 2, then we basically have 2 choices here. If the k value is 2, then I want to make a subarray of size 2. So either you make a subarray of size k here, and if you try to do that, then I will be trying to take the sum 5 plus 1, and then the next index for processing should be starting at index 4, because all the elements from 2 until the I plus k minus 1, everything has been included. So the next index that I want to process is I plus k, because everything is included here, right? This is one option for inclusion. So another option would be to not include this 2. That means I will not start the subarray at this index 2, but I will try from the next index, which is index number 3, and I will see if I want to start here or not. Maybe I will be starting here, or maybe I will not be starting here. So being at an index I, we will basically have two choices: whether you do not start a subarray here, and this is the exclude case, that means the not taking case. And in this particular case, I will be going to the next index, and I will have this much size of the array which is left to be processed, and then I will have certain count number of subarrays to be taken. So in this particular problem, the count value should be 3, because I want to find 3 non-overlapping subarrays. So you might have included some on the left hand side already. So the count will tell you how many subarrays you need to include even going to the right hand side, and how much of the subarray is actually left with you. That means how much of the suffix of the initial array is left with you. Otherwise, if you try to include this, then if here you had a count value, then one subarray is getting included at index I. So the next point of processing will be I plus k, because I plus 0, I plus 1 till I plus k minus 1 will all get included in a subarray of size k. And therefore we will be resuming our same process from index I plus k, but our count value will decrease by 1. Count value will decrease by 1, it will become count minus 1. So you can start your count process from 0 and go till 3, or you start your count process from 3 and go till 0. Both the things are same. You just have to keep a track that you exactly include 3 subarrays. So this is the include case, and if you are including, then whatever is returned from this sub problem, that value needs to be added to the subarray sum, which is 1 plus 5 in this case, right? So getting the subarray sum from a given array is faster when you use a prefix sum, because you know that if you do pre-processing of prefix sum in order of n time, then each of the subarray sum queries you can answer in order of 1 time, because there are no update queries, right? And in this particular case, the sub problem will be defined as what is the size of the array, that means what is the suffix of the array that is left with us, and how many subarrays we are yet to include, because the count will tell you about the number of subarrays you have included or you are yet to include, and the index will tell you about how many elements you have to process, right? All the left hand side elements are already done, so you cannot look at them. So this will be the sub problem, right? So what will be the answer? The answer will be when the index is equals to 0 and the count is equals to 3, or you can say the count is equals to 0, because I will be using count equals to 0 and going up to 3. When I include one subarray, I will be increasing the count. So this will be the entire problem. Index 0 means when you have the entire array, and count 0 means when you have not included any subarray and you have to include all the 3 subarrays. Then what will be the maximum sum that you get? And this problem actually has 2 parts. The first part is getting the maximum sum, and second part is about finding the path which leads to the maximum sum. So let's take an example of having 6 elements and the k value being 2, and let's find out for 2 non-overlapping subarrays. Because if the problem extends to 3, 4, 5 non-overlapping subarrays, you just have to change the value of the count, and this solution will always work for whatever number of non-overlapping subarrays you want to take. Okay, so this is a generalized solution. So let's say that the total number of non-overlapping subarrays that I want to form is 2, and in the code you can just change this 2 to 3 and it will definitely work. Now why we have taken 2 here is so that the recursion tree diagram looks simpler and easier to understand. Okay, if I take 3, it will be a huge recursion tree diagram and it will be difficult to understand. Now we have already seen that we can process the prefix sum array. I have taken one extra size so that all the range sum queries can be solved by just a single formula. That range sum in the range of L to R can be given as prefix sum at R minus prefix sum at L minus 1, right? So if you want to use this formulation, then you will have to take care of out of bound case. So I will just be appending a 0 in the beginning. Right, once this is done, let's understand about the recursion tree diagram. As we have understood that if we are starting at this point I, the node here will be telling me the index. The node, like this 0 here, is telling me what is the current index. So the current index is I. Let's say it is 0. At this point, I can either choose not to start a subarray at this point or to start a subarray at this point. So let's say my first option is not to start a subarray at 0. So where I will go? I will be going to index 1. So I am going from 0 to 1. But my count value will still remain as 0 because I have not included any subarray. Now being at 1, again I can choose whether I want to start a subarray here or I don't want to start something. So let's say I don't want to start. So again I will be going to index 2 and my count value will be 0 because I have not included any subarray yet. Now at this point again there will be two choices, and let's say I took the first choice of excluding. That means I will not start the subarray at index 2. I went to index 3. Now I know that already I want to form two non-overlapping subarrays and I am at index 3 and my count value is 0. So if you find out what will be the minimum number of elements required to actually include two non-overlapping subarrays, it will be equals to 2 times of whatever is the k size, which is the window size. So 2 into 2, it will be 4 elements. But if you look at it, we are at index 3 and we just have 3 elements left, 3, 4 and 5. So is it possible to get two subarrays which are non-overlapping of size 2? It will not be possible. So we do not have enough elements. Therefore we have to return back from here. And what will be returning back? We will not return back 0, but let's say we are returning minus infinity, showing that this case is not possible. Now on the right hand side, like being at 2, this has returned minus infinity as one case. Now again being at 2, we have tried not starting a subarray at this point. The another option is to start a subarray at this point. If I start here, then I'll be including a size k subarray here. I can use the prefix sum and get the sum. So by not including, I got a value of minus infinity. By including, I will get a sum 6 plus I will have to check what the other sub problem is giving me as a sum. So my count value was 0 here, but after including, the count value became 1. So the count will be 1 here. When I reach to index 4, the count value will be 1. And my sub problem will be just having two items. Now again, at 4, I do not have an option to exclude, because if I exclude and go to index 5, then again, we will not have enough elements and it will return minus infinity, right? So this here will return minus infinity due to the same reason as we saw at index 3, right? So it will return minus infinity from the left side. From the right side, if I happen to include this, the sum will be 9 plus whatever I get from index 6. So I'll be making a k size jump to index 6. Now index 6 is out of bound, and if you reach to out of bound, that means we are done and it will be returning a 0 sum. That means we will not be getting any extra sum. So it will be getting 0. So what this 4 will return, out of these two possibilities of include and exclude, we are trying to find the maximum sum. We want to maximize the sum. So it will be taking the max of minus infinity comma 9 plus 0. So this will be returning a value 9. So here you will get a 9. So again, it will be calculating the max of minus infinity comma 9 plus 6. So this will be returning a value 15. So this 15 return value shows that if you have this sub problem, which is saying that we have all the indices from 2, 3, 4, 5 and our count value is 0. That means we have not included any subarray yet. Then I can include two subarrays and my maximum sum will be 15. This is the meaning of this. Okay. Now at 1, I have tried all possibilities by not starting the subarray at 1. So let's start a subarray at 1. If you start a subarray at 1, then you will get the sum of k size, that is 1 and 2. Okay, so that will be 4. What I got from the not including case is 15. If I started this one, the sum will be 4 plus. We have to check what I get from this 3. At this 3, again we can choose whether to start at this point or not to start at this point. So if I don't start at this point, I'll go to 4 and my count value will remain as same. So if you look at the previous 4, the count value with 1, it is the same sub problem, right? It is a repeating sub problem. So I can simply return the value if I have saved the sub problem, and what it was returning 9. So it will get 9 from the exclude case. Now if you include a subarray starting at 3, then you will include 3, 4. So the sum value will be 7. The count value was 1. So the count here will be equals to 2. So at index 5, you have count 2. Now since the count 2 has come, So this is a done case, okay, that we are done. We have already included the two non-overlapping subarrays, so why should we process extra? If we process extra, we cannot include anything. It is not allowed. So immediately we can return a value from here, which is 0. So 0 will be returned. So what is the maximum value here? It is 9. So this will be returning 9. Right. So 9 will be here, and we will be returning the max of 15 comma 9 plus 4. So this will be 15. Okay. So 0 is getting 15 from the exclude case. From the include case, let's see what it can get. So if I include this 0 comma 1, then I'll be going to the next index at 2, and then the count will increase by 1 because we have included a subarray. And so if I do that, then this will be 5 plus, because the sum is 5 here, plus whatever I get from the include case. Okay, so let's explore at this 2. If I don't include this, then I'll be going to this index 3, and the count of subarrays that I have already included is 1. This subproblem was already calculated here, if you see, and this is a repeating subproblem. So the answer is already 9, so this will be returning 9. Okay, so this will be getting 9 from the non-including case, and from the include case, if you include this 2 comma 3, then it will be having 6 plus 6 is for this 1 plus 5 plus it will be getting for to count equals to 2 and at index 4. So when the count is 2, we have already included two non-overlapping subarrays, it will be returning 0. So the maximum will be 9, and so this will be returning 9. So the maximum sum that you get is 15. Okay, so this will be returning 15. So this is the first part of the problem, getting the maximum sum. We got 15. After having got this, the second part of the problem is about finding the path which gives me the maximum sum. So I can easily do it using the greedy selection process. So if you are at this 0, then I have the sum from both the exclude case and the include case. Now in this particular case, I will be comparing which sum is larger. Whichever one is larger, I will make that selection. Okay, being at this 0, whichever one is larger. If two sums are same, that means if include sum and exclude sum are same, then I will always pick the include case, because if I include right now, since I am moving from left to right, then it will always give me the lexicographically smaller start index. Okay, but in this particular case 15 is larger than 14, so I will not include this 0 into my sum. So 0 is not included. So where do I go? I will go to this one. At this point I will be checking the exclude case and include case. So if I exclude, that means 15 is larger than this 13, so I'll be excluding at 1 as well, and I'll be going to index 2. At this index 2, if I exclude, I get minus infinity. If I include, I get 9 plus 6, which is 15. So I will include that this 2 and 2 will be pushed into my path. Okay. Now if I include that 2, I will be going to 4. At 4, if I don't include, then I'll get minus infinity. If I include, I'll get 9. So I'll include at 4. So 4 will be included, and I will be going to 6. And you know that at 6 the count value is 2. So I don't need to do anything. So 2 comma 4 will be the result in our case. So I hope you have understood how to find the maximum sum using the knapsack strategy and the path as well after having found the max sum. So in this particular case, if you apply memoization, then the total number of sub problems will be whatever is the size of the array times of what is the total number of non-overlapping subarrays. In the problem statement, it is 3. So the total number of sub problems will be 3 times of n. This is the total number of sub problems. And since we are not resolving a sub problem, therefore the time complexity will be order of n, because the unique sub problems are only 3n. And the space complexity will be the same as order of n, because we are using an n size prefix sum, and also our memoization table will be n times of 3 size. So if you make a table, a 2-dimensional table, then you will take an n size in the row and the count size as the column, or you can take count in the row and n in the column. Anyway, it will work out. Okay, so this is the time and space complexity. Now if you look at how much time it is taking to find out the path, it will be the height of this tree, and the height of the tree cannot go beyond order of n, right? It cannot go beyond order of n. So finding the path is also order of n. Therefore, the total time complexity will be order of n, and the space complexity will be order of n. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, we have taken the prefix sum array, the maximum sum, the memoization table, which is 2 times of 10 to the power 4 plus 1 for just safety, and then 3 which was the max count value, and then I have taken the maximum sum path to store the final path. Okay, now if you look at the main function, then in the main function we are given the nums array, the k value. So I'll be setting the memoization table with -1 because I know that there will be no -1 values occurring in our answer set since all the values are positive. If you add a positive value, it will always be positive. And since I'm returning -infinity for incorrect cases, therefore -1 is not occurring. The only negative value which occurs is -infinity. I will be calculating the prefix sum, and after doing that, I will be finding the max sum using the 01 knapsack DP. Once you are done with that, then we will do the greedy selection process using the memoization table or the 01 knapsack code and find the maximum sum path. Now let's look at the APIs one by one. So if you look at the max sum, the find max sum, in this case we are getting the nums, position, count and k. So if the count is reaching 3, that means we are done including 3 subarrays, so we will be returning 0. This is a done case that we had seen in the recursion tree diagram. Otherwise, if the position is greater than nums.size minus k, that means we do not have enough items. So this is not enough item case. Then if the subproblem is already calculated, that means it is a repeating subproblem, then we will return the answer. So this is repeating subproblem case. All these 3 cases I have shown you in the diagram, recursion tree diagram, right? After having done this, we know that at node I, that means at the ith index, we have 2 choices. Whether I start a subarray here or I don't start here. So if I don't start here, then from position, which was I in our example, we will go from position to position plus 1, but our count value will not change. And if I start our subarray here, then I'll go from position to position plus k, and my count value will increase by 1 because I have included a subarray here starting at position of size k, and the current slice from position plus 0 to position plus k minus 1, this sum has to be included because we are including the subarray sum here, right? By taking the exclude and include case, I will be taking the max of it and storing it into the memoization table for the subproblem of position and count, and I will be returning it. So this can be solved in order of n time as we explained, and after having seen the maximum sum, we will be able to find the max sum path. Now in the find max sum path, we will get the nums, position, count, k and the path vector. Again, if the count value is 3, then I cannot include anything anymore into the path, so I'll be returning back. And if we have insufficient item, then also we will be returning back. Now there are 2 cases of start and don't start. So get the sum and compare if starting here is actually more optimal, or if it has same sum, then I will always be including the current index as the start of the subarray and process further. Otherwise, if do not start case is giving me a higher sum, then I will be following the do not start case and I will be going to position plus 1. I have already explained that if 2 sums are same for start and don't start, then I will always pick the option to start at this index I, because that will always give me the lexicographically smaller indices. Okay, so this is the entire code and I hope you are able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.